Hi, in this video I'm going to go over a very simple linear programming problem with equality constraint. And the goal is to understand geometrically what's going on when you do stage 1 to put the system in canonical form, and also how duality works geometrically. And this business about equality constraints becoming unrestricted variable. All right, so let's begin. So the problem I chose to work out is a minimization problem. Minimize 5x1 plus x2. Now, of course, a minimization problem is also a maximization problem. I could equally well call this problem the problem of maximizing minus 5x1 minus x2. And for me, geometrically, it's easier for me to understand it this way. But I'll refer to it in both terms. But keep in mind that these two concepts are exactly the same. There's no difference between minimizing a function and maximizing its negative. All right? We'll have exactly the same solutions. And I have these three constraints, two inequality constraints and one equality constraint. And those are graphed here. The first inequality constraint is this red line. And it's easiest, I think, to graph lines by finding their intercepts. The x-intercept here set x2 equals 0. X1 intercept is 5. X2 intercept is going to be 1. This one, the x1 intercept is going to be set x2 equal to 0. That's 1. X2 intercept will set x1 equal to 0. X2 is 4. Okay, so you can see the red line is the first and the green line is the second. And then this is an equality constraint. So this one has slope -1, and that's the light blue line here, the cyan line here. All right, so we've got our constraints. Now notice that these are less than or equal to constraints. So the feasible region is below the line. It's below this line. It's below the green line, and it's on the cyan line. So the only feasible region is this line segment. Okay, that's the set of possibilities. And here x1 and x2 are positive. Okay, all right, so we've graphed it like this. Now you remember geometrically how to solve linear programming problems. You look at your feasible region, you find the extreme points, and you find where the objective function is optimized among those extreme points. Now, in this case, I have two extreme points, the two ends of the segment, so it's an easy matter to just check the objective function at those 2 points and find out where it's smallest if I'm doing the minimization problem. Now, geometrically, what this means is that the gradient direction or the direction of maximum decrease, in this case, maximum decrease of 5x1 plus x2, is this purple line here. Okay, and I want to decrease as much as possible. So I can think of this constraint here as a sliding line, slide it parallel. As I slide this line parallel farther to the left, the smaller this value will be. So I want to find the point in my feasible region that makes this smallest, so it should be the point where I can slide this line as far as possible to the left and get an intersection. And that's going to be this point here. And the interpretation of this is that if I look at the constraints at this point here, right, this point as the extreme point of the feasible region. If I look at the constraints, well, I have this red constraint here. I actually have two cyan constraints here. There's the greater than or equal to and the less than or equal to constraint. One refers to above the line, one refers to below the line, and they both include the line. It turns out that this gradient vector, or this direction of maximum decrease, can be written as a positive linear combination of the gradients of the constraints. A positive linear combination is the gradients of the constraints. So you can see this red line, the gradient of the red line is this direction. You get the gradient by taking the coefficients of the objective function. And so you can recall that the the coefficients of a line give you a direction that's perpendicular to the line. All right, so the gradient is going to be perpendicular to the line, so that's this one. And then the two constraints that make the cyan line, well, one goes down perpendicular and one goes up perpendicular. So you can see, in fact, this is where the unrestricted comes from, because the coefficient of the gradient could be in this direction, or it could be in this direction, which is like positive or negative. And we'll see that shortly, how that works out. But in this case, this direction of maximum decrease is the positive linear combination of this vector here, which is a multiple of the gradient of one of the cyan constraints, plus this multiple of a positive multiple of the gradient of the red constraint. Okay, so so that works out consistently, and everything here I think is okay. I worked out the points, and like I said, the blue arrow here could go in either direction, because you have one constraint whose gradient points down, one gradient whose constraint points up. Okay, now we typically represent systems like this in two different ways. We have the standard form that we use for the simplex method, and we also have the inequality form that we use for duality. So let me start with the inequality form and show how that relates to this geometry. All right, so the inequality form, it really is very similar to here, and I'm going to use the maximum form because then I can use less than or equal to constraints. So I have I'm maximizing this function minus 5x1 minus x2, and I just take these inequality constraints as they are, and this gives me two inequality constraints, x1 plus x2 less than or equal to 1, and minus x1 minus x2 less than or equal to 1. So what's the dual problem to this problem? Well, that's what's shown over here. I'll have to pull it in just a little bit to make it fit. So before we do the dual, I need to fix some things here. This is a 1.5, and this is minus 1.5, right? Because to get that less than or equal to here, I need to negate the inequality. So this is less than or equal to minus 1.5. All right? We get the dual as a minimization problem because the original problem is a maximization problem. We get the coefficients of the minimization function by taking the constraint constants from the original problem. 5, 4, 1.5 minus 1.5, 5, 4, 1.5 minus 1.5. Notice how the y3 and the y4 have opposite signs and have the same coefficient. And in fact, we can combine them into a single variable. All right. Then the equations in the dual problem are obtained by reading the columns down from the original problem. Right. The coefficients come from the columns in the coefficients of the original problem. 1, 4, 1 minus 1, that's what we have here. And 5, 1, 1 minus 1, that's what we have here. And then the constants become the constants in the original objective function. Okay, so inequality and dual problem. And as I mentioned, this equality constraint turned into two inequality constraints, which gave me two variables. That these two variables can really be combined into one. Okay, so the equality constraint gave rise to an unrestricted variable. All right, so that's the dual problem. Now let's see how this would be solved using the simplex method, this problem. So let me zoom in a little bit because we don't need it quite so big. And a little more maybe. Okay. All right. So we can see the standard form. I'll go back to minimizing, the minimizing form. We're minimizing this function, 5x1 plus x2. I need to introduce these slack variables. Okay, so this is the first inequality constraint with a positive slack variable, second inequality with a positive slack variable. Then the equality constraint I can write as two equalities here because I need to ensure that the variables are positive. x1 plus x2 greater than or equal, x1 plus x2 less than or equal to 1.5 can be written as x1 plus x2 plus x5 equals 1.5, and all of these variables are positive. x1 plus x2 less than or equal to 1.5 can be written as x1 plus x2 minus x6 equal to 1.5. So I get both of these equations here from the original set of equations. So now we're ready to put this into our tableau. But first, let's relate this to the geometry of the situation. Okay? We know that the optimum point is going to be here. So we can predict the result of our simplex algorithm. Right? This x3 is a slack variable for the red inequality. The x3 is going to be 0. All right? Now, what about x4? x4 is a slack variable for the green inequality. The green inequality is not satisfied. So the x4 will not be 0. So let me write that in. x4 will be non-zero. What about x5? Well, x5 is one of the slack variables that comes from this equality constraint. And this equality constraint is satisfied. So both slack variables will be 0. So x5 is 0. x6 is also 0. This is a mistake. It says non-zero. Let me fix that. So there we have it. Now, x7 is an artificial variable that we'll talk about shortly. Now, how many basic variables are there? Well, we can count the variables that have non-zero values. x1 is not going to be 0. x2 is not 0. x4 is not 0 because that slack is not 0. And it looks like those are the only three basic variables. But in fact, x6 is also a basic variable. And the reason is that to make the gradient direction, we needed to include we need to include the gradient of the constraint from the last equation. So that means that that's also going to be a basic variable. Okay, so let's just go and look and see how the dual problem would be expressed in standard form. So I'll move this over here. Right, this is our dual problem. And here I've grouped together the y3 and the y4. Now this greater than or equal to constraint, I've transformed into equality constraint by adding a slack variable. Right, this is a positive slack variable. So what I had to do was flip the signs to make this a less than or equal to and add a y5. Similarly, with the last one, I had to flip the signs to make this a less than or equal to inequality. And then I added a positive slack variable. Now notice that these two equalities can be written as a single vector equality, where each vector is R in R2, right? So this one, I have this slightly wrong. This should be -1, -5. This should be -4, -1. This should be -1, -1. And this also could be -1, -1. And these have to sum together to give -5, -1. Now, what's going on here? This is exactly the situation that we have up here, right? Where we had to get the sum of this vector here as the positive sum of two different vectors here. Okay, and this equality is playing out in the dual problem. Let me move this over a bit so you can see it. All right, so that should be visible. You see how the gradient vectors are adding together to give this direction of descent. Okay, so let's go ahead and solve our original problem using simplex. Now we get into the stage 1 and stage 2 aspect that we need to introduce an artificial variable. So what's going on with this artificial variable? At the beginning, in our original setup, we don't have a basic feasible solution. This is because I can't set all the singleton variables equal to 1 because this x6 has a negative coefficient. I can get x3 equal 5, x4 equal 4, x5 equals 1.5. Negative x6 equals 1.5. That's not satisfied. Now, of course, that would correspond to the solution where x1 equals 0, x2 equals 0. And that does not satisfy the constraints. So what do I do here? What I do basically is I add a slack variable so that this does satisfy constraints, and then I try to minimize that slack variable so it goes back to 0. Okay? This x7 can be thought of as a slack variable that expresses the difference between this solution and the unsatisfied constraint. You can see, in fact, 3 of the constraints are satisfied. The red constraint is satisfied because it's a less than or equal to constraint. The green is satisfied also because it's less than or equal to. One of the cyan constraints is satisfied. It's only one of the cyan constraints that's not satisfied. Okay, so as I said, I introduce a slack variable that expresses the fact that the constraint is not satisfied, and then I try to make that slack variable 0, and that will take me back so that the slack variable is satisfied and I get a feasible solution. So that's what's happening in the first stage. So here I'm using the LP Assistant from the book to solve my original Tableau, and you just go ahead and do the regular pivots here. When I set this up, it set up a single artificial variable, just as I have up here. And then just go through the pivots directly, and you end up with this solution. Now notice what the coefficients down here represent, the 1 and the 6. By the way, these equations down here are, I was just figuring out something, so we can remove those. All right, so what does the 1 and the 6 down here represent? Can you see that? Let me make it a little bit bigger to make sure you can see it. Okay, the last row is 1 and 6. So where did those come from? Well, we started out with this Tableau. Remember the 5 and the 1, those are the coefficients of my original objective function. The 1 and the 5 here, those are the coefficients in the first inequality constraint. 4 and 1 in the second inequality constraint. The 1, 1 is the equality constraint. This also is the equality constraint, but I have a -1 here. So this last row I could think of as -1, -1, 0, 0, 0, 1. I could think of it that way. So here I have the inequality constraint. When I'm doing pivots, what am I doing to the last row? I'm taking multiples of these rows here and adding it to this row here. So what I'm doing is I'm taking multiples of the gradients of the different constraints and adding it to the gradient of my objective function. Okay. So what this means, for instance, is that if I take -1/5 of the gradient of the first constraint, 1, 5, and add it to the gradient of the objective function, 5, 1, then I'll get 24, 5, 24 fifths, and 0. Okay, so this row here, this top row below the line, is always expressing an equality relating the gradient of the objective function to the gradients of the constraints. Now, in the end here, I get 0, 0. What does that mean? That means the gradient of the objective function is equal to some combination of the gradient of the constraints. In fact, this is saying that 5, 1, so I can say, in fact, it's -5 minus 1 is equal to 1 times the gradient of the first constraint plus 6 times the gradient of the last constraint, which is going to be -1 minus 1. So you can work that out. -1, so -5 minus 1 is equal to -6 minus 6 plus 1, 5. All right, and that's exactly the equality that's expressed here. All right, the gradient of the objective function here is equal to the sum of gradients of the constraints. All right, so that's why we can read off these values from here, and this actually corresponds to the solution of the dual problem as I showed up here. So let me make one final correction here. I did make an arithmetic mistake here. When I did this here, I have this minus 5 here, when I change the sign on this equation here, these are not negatives, they're positives, all right? So I do get positives here instead of negatives. So you can cross out all those negatives, and I am in fact getting y1 times 1, 5, plus y2 times 4, 1, plus y3 times 1, 1, plus y4 minus y4 times 1, 1 is equal to minus 5 minus 1. And you can check that if I set y1 equal to 1 and y4 equal to 6, I exactly get this result, which is the same result that is expressed in the last row of the final simplex tableau. There, I corrected the signs here so that it's correct. Now you can verify that if I take, let's get this here, if I take y1, well, yeah, let's do this. Okay, y1 is equal to 1, and then y4 is equal to 6. This will satisfy the above equation. Okay, and it's no coincidence. In fact, I hope that you were able to follow my argument that that's exactly the expression that's expressed in this final tableau, where the 1 and the 6 correspond to my 4 accessory variables. Okay, so I hope the takeaways here are, if we go briefly back over, the system of inequalities does correspond to a geometrical arrangement of hyperplanes, and there's a relationship between the hyperplanes and the normal vectors to those hyperplanes. And this is a dual relationship. At the optimum point, the gradient of the maximum function, or for a minimum problem, the direction of maximum decrease, the gradient is equal to a positive linear combination of the gradients of the constraints that hold at that point. And what that means is that the corresponding slack variables to those constraints are 0 in the solution. Right? And this is reflected in also the duality. Duality is expressing the relationship between this problem with gradients and the original problem. Right? One thing that tripped me up when I was making this video is that please remember that when you're doing the dual problem, you do not use standard form, you use this inequality form. Okay, so keep the two different forms separate from each other. Inequality form uses inequalities in the expression, but standard form, of course, converts that to equalities. Right. But the nice thing is that these are two different ways of looking at the same thing, and we have two different ways of getting the result that the gradient of the objective function is the sum of a positive linear combination of gradients of some of the constraints. We get that here from this tableau, and we also get that from the dual problem. Okay, so very beautiful, a lot of things tied together, and it's worth thinking about this to really deeply understand what's going on with linear programming. Thanks for watching.